Welcome to follow up. Let's have a look at problem 880, decoded string at index. In this video, we are going to solve this problem using Euclidean division. So the plan is the following. First, I'm going to read through the problem statement to digest the requirement. And then we do the coding according to our analysis. And finally, we walk through an example. So now let's look at the statement. So we are given an encoded string S, and the way to decode it is the following. So if the character read is a letter, then the letter is written onto the tape or output. If the character read is a digit D, then the entire current tape state is repeatedly written D minus 1 more times in total. In other words, the current state will repeat in total D times. So given an integer k, we want to find the kth letter in the decoded string. So here we want to emphasize that the problem requires that we use one indexing convention. So now let's look at the three examples. I'm going to look at them reversely. In example 3, so k equals 1, so the first letter is the character is a letter, so we just return this A. In the second example, we have HA repeated twice, then we get haha, then haha repeated twice, so we're going to get haha, haha. So in this case, k equals 5. So this haha is modulo. If you modulo 4, you get 1. So this 1 corresponding to this h, right? This is the return. In the first example, you can actually decode the string. It's leetcode repeat 3 times. So then, if you look at this copy, leetcode, it already contains 12 characters larger than 10, right? So we just slice the 10th one. That is leet, this 8. So we get C, this 9, O will be the 10th one. We're going to return O. So later in our analysis, we're going to further digest this. So the constraints basically says that the length of S is bounded above by 100, and S consists of lowercase English letters and digits. So digits are from 2 to 9, right? So S starts with a letter, right? This is for consistency, and also k is less than or equal to the length of the decoded string. The last one is also a length. So this is the largest bound for 64-bit integer, right? So here the main observation is the following. So main observation. So if we have a letter, let's see, we have leet, and then we repeat 4 times. So we're going to get leet, 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 and leet. So if k equals the 5, so we should return this L, right? So because this string is a repetition of a base, let's say this leet, right? So in this case, so we just need to modulo that one. So for example, this k modulo this 4, that is 1, right? We just need to return the first one. This is the L, right? So if you look at others, let's see, k equals say 6, 7, right? So if you look at k equals 7, so what we want to return is this E, right? So this leet contains 4 letters. So then the third one in the second copy will be the E. So this, if you examine this modulo operation, you are going to get a 3, right? So this is basically our main observation. So we want to encode this observation using Euclidean division. So here, let me first write a naive one. Basically, we want to see this cannot pass the test cases, and then we optimize it a little bit. So here, we are going to have a size. Let's call it 0 originally, right? And the current string as current state, so it's also an empty one, right? Then we are going to scan the string. So for character in S, right? So if character is so it's alpha, it's a letter, right? So in this case, so we're going to do current equals current plus this character, and then the size is increased by 1, right? So if size is greater than or equal to k, right? So we just need to return the current at k minus 1, right? So this is another one case. The other words, so if this character is a numerical number, then the current will be current times integer character times, right? So in this case, the size is amplified by this integer character, right? So again, we can do the check. So basically, we can do this check like this. Cut this one here after we adjust the size, and then we do the return. So because of the assumption of this problem, it's guaranteed that k is less than or equal to the length of decoded string. So this must return something. So now let's do a test. So in this first example, it passes, we get O, and for the second one, we should expect we get H, right? It also passes this one. Now let's look at this one. This is very special, but we want to verify it's right. So we're going to get A, right? But if we submit, what we get is that the memory limit exceeded because this is too large, too long. But for this problem, if we take into consideration of Euclidean division, actually we don't need to specifically decode the string or write into memory. So now let's copy this one, and then we want to use the idea of Euclidean division. I'm going to change this one to be V1. So I'm going to mark that this memory limit past accessed. So now for this real solution, what we want to do, similar actually. The idea is the same. So the size, then we are going to get the full size of this decoded string, but we don't compute the decoded string. So here for character in S, so if character is alpha, right? So in this case, I'm going to increment this size. Otherwise, I'm going to amplify the size by this integer of this character. Then for this, we're going to get the size. So let's print out the size. So for let's use this second example to digest, because this will give us 8, right? Yeah, we get 8. So now let's look at the main strategy. So we want to use Euclidean division. So how we do this? So actually we can work or iterate backwards. So here for G in range, I see length S, -1, -1, and -1. So this is the largest index. So we end before -1, that is 0. So the increment is -1, it means decrement. Then in this case, because of this observation, right? So we are going to first do a modulation, right? K modulo the size. So in this case, after we do this operation, so it's guaranteed K will less than the size, right? It's greater than or equal to 0 and less than this size. So this we check. Actually, also we need to take into consideration here we are using y indexed, right? So now the criterion is this: if k equals 0, right? If k equals 0, it means the current k, you can think it's a multiple of the size, right? Like here we have a lead, and this is the size, this is the 4, right? If we want to compute the 8th one, you are going to get this, right? So this t. So if k is 0, and so s and this character is alpha, then in this case we're going to return the current character. So this is the one case. for the other case, if this is not right, then we consider whether SG is a character or it's a digit. So if SG is alpha, right? So in this case, so the size will be decremented by 1. Otherwise, it's numerical corresponding to an integer or digit. So we're going to shrink the size to be int the current SG. So this way, due to the assumption here, so it will return the corresponding number. So now let's do a test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So before we end this video, let's walk through one example so that we know we genuinely understand this problem. Let's use this one. So here, right, so we can compute the size. So if you look at this, the size will be 4, then double, this will be 8, then plus this code, that is 12. 12 times 3 is 36. So we get 36 for the size initially. And also we want to find k at integer k equals 10. So then first, if we look at the s, we first look at character equals 3. In this case, if we look at the k modulo this size, that is 10 modulo 36. So this is still 10, right? So this k is not 0, so we don't do a check, but we just shrink the size. Because this is a corresponding to a digit, then the size will be, so next is after we finish this, so the size will be the original size modulo divided by this 3, that is 12, right? So now let's look at another character, that is e, right? So in this case, let's first compute this k. So k modulo let's see 12. So this 10 modulo 12 is still 12 because k is not 0, right? We want to check this is the e, then the size will be 12 minus 1, that is 11. In other words, after we finish looking at this character e, the size will be 11. So now let's look at the previous character, that is d, right? So now let's first compute this k modulo 11. This is still 11, right? And then because d is a character or letter, then the size will be 11 minus 1, that is 10. So now let's look at the character o, right? So the character o, so let's first compute k equals 10 modulo 10, that is 0, right? So in this case, this character is also a letter, so we return this o. This is the walkthrough for this example. So here, this condition, we check k equals 0. This due to the fact that we are using y indexing. Right. So if you consider using 0 indexing for this, for example, this one, the fifth one, right? So you can use actually for k equals 5, you can use the 5 minus 1. So we change to 0 in 5 minus 1 will be 4, right? Then 4 over 4, that will be 0, right? Then it corresponds to L. You just return this L. So similarly here, right? So you look at the seventh one. If you're using 0 indexing, correspond to 6, and then 6 modulo 2, that is not modulo 2, modulo 4, that will be 2. Then 6 corresponding to E, right? This one, and then you can look at this one, the same thing. So you get E. So this E, right? This is index 2. So with that said, that's basically about it for this this video. So the key thing is that, so we look at this condition and get the corresponding return. So with that said, that's about it for this specific problem in the video. Thank you.